Okay.
Okay. Yeah. So hello everyone. Today we'll be talking about homothety. So before we proceed, obviously we should define what homothety is. So to give an analogy, imagine you're standing at a point P, and let's say you're holding a camera in your hand, and what you do is you basically zoom out by say 2 or something. So what would the position of some other point Q that you're looking at, where would that end up? It would appear closer, right? So where it would show up at the midpoint of PQ. So this would be like the projected image. And obviously, like if you're taking a picture of a certain shape, then no matter what zoom you take it with, the shape remains that shape. And this analogy is basically what homothety is based on, loosely speaking. So let's go into the formal definition. So a formal definition for a homothety is a homothety can be defined using a point P and a non-zero real number K. And what you do is you say that the homothety is centered at P with ratio K or factor K. And what that means is if you have a point X, then X will end up at a position X prime on the line Px, so that Px prime over Px is equal to K. This is in sign distances. So for example, if K is positive, let's say K were equal to 2. So then if you start with P and you have X, then that ends up at this point and these two are equal. So you basically reflect P over that point. Obviously, you can choose K3 and all. If you take K equal to something negative, so what that does is it basically sends it in the opposite direction. So basically, let's say I select minus half. So then it would go to this point, Px prime. So that P lies between X and X prime, and you have Px prime divided by Px equal to half. So when you treat it in sign, it becomes negative. So that's the definition. Some special cases when K is equal to -1, that is just reflecting over P, right? X ends up at its reflection in P. And of course, like I said, when you have K equal to 2, you end up in P's reflection over that. So you'll often also find people saying dilate at some point with factor something. So that just means they're having a homothety centered at that point with factor K or whatever number they say. So
here P is the homothety center, right?
yeah, P is the center of the homothety. That's right. Okay. So first of all, like we said that in a homothety. So a homothety is basically a mapping of the Euclidean plane to self. And basically we can let's call it as some function. Let's say we call it h of p comma k, right? That's the homothety centered at p with factor k. Now this satisfies some things like the shape should remain the same shape. Let's try to quantify that. So imagine you have like a triangle and you have a point P and you have this ABC. So what happens when you say take K equal to, let's assume 3 for now. So in that case, okay, maybe 3 is a little too big. I don't know if I have space. Let's select 3 by 2 maybe. So you have something like this, right? This is where A ends up. This is where B ends up. And that's where C ends up. And something important to note is that A prime, B prime, C prime is the same shape as ABC, which means that they're similar. Can anyone quickly prove this?
What to prove?
That ABC and A prime, B prime, C prime are similar.
The sides are proportional, so we are done by SSS.
Yeah, that would work. The sides are proportional. And why are the sides proportional?
That is due to the homothety, na? Because they are projected.
No, but we don't know homothety yet, so you can't use any properties we haven't proven yet. So you'll have to prove that as well. We only know PA by PA prime is K. Like sorry, PA
Okay,
prime
so
by PA is K.
firstly, like
We can say that
we can say that BC is parallel to B dash and C dash.
Yes, very good. So because we have this, let's take a look at this, just 2 points. So you have A and B, and you have P. Now, when you extend by the same ratio, you have PA by PA prime is PB by PB prime. And so AB is parallel to A prime B prime. This is also known as Thayer's theorem, but it's really just similar triangles along with a common angle. So you do your SAS here. You have these two in proportion, and this angle is common. So the two are similar, and so you also get AB parallel to A prime B prime. And once you have that, you just get that all three sides of these two triangles are parallel to each other, and so the angles are equal. And so it's similar. And of course, like someone said earlier, you can also just observe that AB by A prime B prime is equal to some fixed constant 1 by K because of just this similarity again. And of course, now if you have any random arbitrary shape, how can we prove that it will end up? Okay, let's assume the shape is continuous or made up of continuous curves for now. So how would you prove that it ends up it ends up in a curve that is similar to this? So the way to do that is to just approximate this curve by using very small segments, and each of these segments ends up in something similar. And you can prove this for you can repeat this argument for any sequence of segments. And if you just make finer cuts into this figure, you'll eventually prove that it maps to something similar. It's not very rigorous, I understand, but this is more or less the general idea of why things stay the way they are. Another thing we observed here is that any segment maps to another segment which it is parallel to, right? So in general, this tells you that if you have a line and a point P, then the homothety will send this line to another line which is parallel to it. So basically, homothety preserves direction or slope, whatever, right? Okay, cool. Now, it also, in fact, preserves interactions between two different objects. So, for example, let's say you have some random object and some other object. They're intersecting in, say, 2 points. So any homothety, when you consider wherever this curve maps to and wherever this curve maps to, the intersections of those two will be exactly the points where these two end up. This is all very natural to expect, and it's just true. So I'm just stating it. But of course, you can use this to obtain some very interesting results. For example, let's say you have some circle and you have a line tangent to it, and let's say you take a point P and you dilate, right? Then this will end up in some circle, and the line will also end up in some line. And what you can see is that this new line and this new circle, they will also be tangent, and they will in fact be tangent at the same point. In fact, sorry, the tangency point will be the image of the tangency point in the pre-homothety figure. So this is all just seeing how it basically is the same thing, but of course with different scale. And homothety is of special interest, especially when your expansion sends these points to things that are also there in the original diagram. So it allows you to see them in a different way. Let's see an example to understand that. So let's say you have a circle. You have this, right? And you have a circle inscribed in here. So this touches over here. Let's say this point is T, and this is X. And let's say you have another such circle. So this is T prime and this is X prime maybe. So we can prove that Tx and T prime X prime meet on the circle. Okay, so to prove things like this, it is of special interest to understand how like if you're given two similar objects, how can we locate the point of homothety that maps one to the other? Or rather, when can we do it? So more generally, let's say we have some figure F1. Let's assume it's a triangle for now. And let's say there's another triangle. So when is there a homothety mapping the first triangle to the second triangle? Anyone?
When both the triangles are
Extending the
similar.
line joining the vertices.
Okay. We have some interesting ideas here. So let's name these. Let's call this ABC. Let's call this DEF. So what are the set of conditions we need?
The corresponding sides are parallel.
Okay. So we need AB parallel DE, and we need BC parallel EF, and of course we also need CA parallel DF. So we obviously need this. Is this also sufficient? Is it true that if you have two triangles like this, then there is a point that maps ABC to DEF?
Sides can be disproportionate.
Sorry?
I guess no, because the sides can be disproportionate. I think so.
Okay. Well, first of all, if they are parallel, then the angles are equal, right?
Then it works. Then it works.
And then so then they're similar. Yeah. So that's not the issue.
Then it works.
Okay. So someone is saying that AD, BE, and CF will concur, and they will concur at the point of homothety, right? Okay. So first of all, why are they concurrent? Or rather, let's assume they were concurrent. Is it true then that there is a homothety at P sending ABC to DEF? In fact, let's even make this even more simpler. Rather than focusing on triangles, what if we think about a segment and another segment? When is like what is there always, first of all, a point P that sends AB to CD?
Yeah, if and only if AB is parallel to CD.
Yeah, of course, AB has to be parallel to CD. But if you know AB parallel to CD, is there something that sends segment AB exactly to segment C?
Yes, there has to be a point because it's like a triangle and a BPT. By BPT it works. I guess so.
They should not be congruent. Yes, that is also correct. Otherwise, K would be equal to 1, and then you wouldn't have any expansion.
Yeah, like you can apply the BPT, basic proportionality theorem, and the converse of BPT works. That when two lines are parallel, there will be a triangle forming, I guess.
I'm not quite sure what you mean. Like, can you tell me how to locate the point P which sends AB to CD? I'm just interested in that.
taking the intersection of AC and BT.
Yeah, exactly. So because A is mapped to C, so it should lie on AC. And because B also maps to D, it should lie on BD. So if any point works, it had better be this. And we can see that because now PAB and PCD are similar due to being parallel, you can just choose ratio CD by AB. And when you expand P with that, the segment maps to the segment. And so for two segments, we can figure it out easily. Okay, and what happened? And okay, one thing to note here is that if I demanded B should end up at C and A should end up at D, then we would have taken this. Right? And this would actually be a negative homothety because you're sending B to C with some negative ratio and A to D with some negative ratio. Okay. So that's how you can map segments to segments. So applying this to the triangle case, you can fix two segments. So let's say I fix these two. Obviously, they're parallel, and so I can locate their intersection, and this P will send BC to B prime C prime, right? But I don't know anything about how it relates with A and A prime, even though I know that AB is parallel to A prime B prime and A prime C prime is parallel to AC. So now what I do is I consider this homothety that sends BC to B prime C prime, and I look at A's image in that. So in some sense, we're ghost pointing. So you have something like A double prime, and that's the image of A in this homothety. And now we observe that B prime A double prime has to be parallel to AB, and C prime A double prime has to be parallel to AC. And so you end up getting that B prime A prime is parallel to B prime A double prime, and the same for the other. So you basically get that B prime A double prime are collinear, and so are C prime A double prime. So that would actually end up implying that A prime, B prime, C prime are collinear. But obviously that is not the case, and so A prime should actually be equal to A double. And so this homothety also maps A to A prime, and so the triangle maps to it. So great. So if we have two triangles, we can always figure out a way to send one to the other, right? Okay, now let's move on to more interesting curves. Like what if we have two circles? So let's say I have one circle and I have another circle. And let's say I call this omega 1 and I call this omega 2. I want to locate a point P such that there is an expansion at, a homothety at P sending omega 1 to omega 2.
Intersection of common tangents.
Okay,
Uh,
intersection of common
We could
tangents.
also take two distinct points on both the circles and join the centers.
Okay. We have some ideas. So first we should mark the centers. And
We can choose distinct points on omega 1 and omega 2, and then we can join them, like the O1, O2, and distinct points on both these
okay, so
circles.
let's say we select X here and we select Y here, and I join them. Is this what
No,
you mean?
like, no. Continue O1, O2 as well.
What do you mean continue over? Oh, you mean like draw line over or two?
No, like, okay, Y you should put like a little to the left.
So you're trying to quantify something, so you have to figure out what that exact condition is.
Yeah.
Yeah. Okay, someone also said common tangents. Okay, fine. So these two will have common tangents. Okay, let's accept that for now. It will have internal ones as well, but let's say we're only interested in the external ones for now. Okay. So you're saying that S is like there is a homothety centered at S that sends omega 1 to omega 2. Yes, that is correct, Nishkosh.
Uh, like another homothety can also happen. Like if you take 2 points on omega 1 and omega 2 and join them, and then you join the O1, O2 line. So like
Right.
that point would also take it.
I see. Okay, we'll get there. We'll get there. Also, someone suggested the external tangents idea. So why does this work? Do you have a proof in mind?
Here, what do we need to actually prove to show that they are homothetic? Like, we need to prove that the point where the tangent is touching omega 1 and omega 2, in the two different points, they're equal. Like, so,
No, your job is to find me a point S such that there is some ratio such that omega 1 maps to omega 2 when I take a homothety at that point S with your ratio.
no, I also think S is the point. I wanted to ask that what are the ideas to prove that S is the point?
Yes, okay. So exactly. The first question is to ask what should S satisfy to get two circles, because managing all the points of the circle is difficult, right? So, okay. So first of all, the centers of the circle should map to each other, right? So S should map O1 to O2, like the homothety. Let's call it H. So H should send O1 to O2, right? This is the first condition. And what is the other condition?
the points, suppose the 2 points that the tangent is touching omega 2 is y1 and y2. So and the omega 1 is x1 and x2. So x1 should be mapped, y1 should be mapped to y2 and x1 should be mapped to x2,
Why is that?
because it's because the points, yeah, because they're the common tangents, right? So they have to be mapped to.
Okay, so no, let's think about it this way. You told me that S is a center, right? Or you believe whatever, I don't know. And so you should supply me a ratio and then prove that that ratio sends omega 1 to omega 2. So what is that ratio?
But isn't that just the similar triangles O1 x1 S and O2 x2 S? So like that should happen.
Okay. So
O1 x1 upon O2 x2 would be the ratio of the radii. So that should be the
right.
ratio.
Yes, exactly. So let's discuss that in a more, let's say, formal way. I'm not sure. So h of O1 should go to O2. So because when you have a point P and you send a point Q using a homothety to Q prime, these three are always collinear, right? By definition. And so if h of O1 goes to O2, the center of homothety first needs to lie on the line O1, O2. Somewhere. We don't know, right? And can anyone tell me what the ratio of this homothety will be, or the factor? Because someone just pointed it out a little while earlier.
In this case, it would be the radii of omega 1 upon radii of omega 2. Like,
The opposite way, but yes.
yeah,
So
opposite,
let's
yeah.
say this has this has radius R2 and this has radius R1. Then the ratio or the factor of the homothety should be R2 by R1. Why is that? Because this circle is mapping to this other circle, right? And they are similar. And we know that the ratio of similitude between the two similar figures that you get in the homothety, that is equal to the ratio of the homothety. And so R2 by R1 should be equal to whatever K you have. And here, if we use this point S as our way of determining that ratio, then it's just SO1 by SO2. Sorry, SO2 by SO1, right? So what we want to do is locate a point S on O1, O2 such that SO2 by SO1 is some fixed ratio, right? So how many such points are there on O1, O2?
There could be infinitely many.
Okay, why would that be the case?
No, actually, could you repeat the question?
You have this line O1, O2, and you want to find a point S on that line so that SO2 by SO1 is equal to this fixed ratio R2 by R1. So how many
Yeah, so
such
that,
points are there?
yeah, there will be only one because like we have similar triangles, right? S2, SO2, X2, and SO1, X1.
Yeah, but you realize this is a slightly circular argument because you don't know S is the tangency point yet. So you don't actually
Okay.
know that S, X1, X2 are collinear or anything like that.
Oh, okay.
I think there will be two.
Sorry?
I think there will be 2 points.
Okay, there will be 2 points. That is correct. So first of all, there can be two possibilities. So one is, let's say S lies outside segment O1, O2. In that case, if you simply assign this some distance d and this x, you can solve for x using this. You'll have something like x by x plus d is equal to R2 by R1. And if you do something, you'll get that there's only one value of x which works. And so there's only one such s. Or the other case is s lies inside. And in that case, you'll get another point if you solve x and d minus x. You'll get another point which lies inside the segment, which satisfies this. So what do these 2 points satisfy? They satisfy that if I pick that point and whatever ratio I'm getting, R2 by R1, and when I take a homothety centered at that point with that factor, omega 1 will map to omega 2, right?
Yes.
Okay. And it is at this point that we can also prove it by using an argument that was earlier suggested, which is you pick a point X on, okay, wait, this is O1 and this is O2. So you pick a point X over here and you pick a point Y over here such that these two are parallel. right? And then you take xy intersection O1, O2, and you call that point S. And you'll find that SO1 by SO2 is equal to Sx by Sy, which is equal to XO1 by YO2, because these are similar, right? Because these two are parallel.
Yes.
And because these are parallel, you actually will now end up getting that SO1 by SO2 is equal to R1 by R2, or that SO2 by SO1 is equal to R2 by R2, which is exactly what we
Yes.
wanted.
This is the X similar center, right? And like if it's in between both
I'll
the
get there.
circles,
I'll
then
get
it
there.
would be
Okay.
okay.
Yeah.
Okay.
So now we took a parallel line through O1x, right? Sorry, through O2 parallel to O1x, right? And this intersected Y. But this also has another intersection, Y prime, let's say. What happens if we take the intersection of X, Y prime with O1? What is this point? If you think about it, this also satisfies because S prime O1x and S prime O2Y prime are also similar. So you do have S prime O1 by S prime O2 equal to R1 by R2 as well. And so you do have this condition. So this is the second point we were earlier talking about. Right?
Yes.
So these two both have homothety centered at them that sends omega 1 to omega 2. So the one that lies outside segment O1, O2 is called the X simile center of the two circles, omega 1 and omega 2. And this is called the in simile center. For those of you who are familiar with cross ratios, you'll realize that this is equal to -1. This is a harmonic bundle. But anyway, I won't go too much in on that. And using this, we can also prove now that the common tangents meet at the center of homothety. Because you can just, yeah, so that bundle is harmonic because S prime O1 by S prime O2 is just equal to R1 by R2, which is also equal to SO1 by SO2. Of course, there's a negative sign here, and there's a positive sign here. So the one thing to observe as well is that this X simile center, it sends omega 1 to omega 2 with a positive ratio. Whereas this in simile center sends omega 1 to omega 2 with a negative ratio, right? Because X maps to something not on segment Sx. Sorry, not on ray Sx. So this one has negative ratio and this one has positive ratio. The positive one is called the X simile center and the negative one is called the in simile center. And yeah, like I was saying, you can now also prove this because you know that we can prove that O1, O2 concurs with these two external tangents by simply reflecting, say, and these two are both perpendicular to this common tangent, and so they're parallel, and so this is just a special case of X actually. In fact, you'll observe that here when we take the other two tangents, the point where they meet is the in simile center. Now, because of this definition that most people have in their minds, they make important mistakes. Yes, they will pass through. That's right. That's right. And we can prove that because these two are similar, right? If you take X prime over here and Y prime over here, I think I'm over labeling, but that's okay. So you can see that O1x X prime and O2 Y prime are actually similar because of all the parallel conditions and the isosceles condition. And so they're similar. So S is the center of similarity for them. Anyway, so the common misconception that people have by this definition of thinking about X simile centers as intersection of external tangents or internal tangents is that when internal tangents don't exist, they end up believing that the in simile center does not exist. This is not the case. So if I have two intersecting circles, just because they don't have internal tangents does not mean the in simile center does not exist. It very much does. And the way to locate it is the same. You take some ray which is parallel, let's say X, and you take another one, Y, and XY intersection O1, O2 is the insim. Okay, now let's take a look at some special cases. For example, what happens when the two circles are tangent? Let's say they're tangent at some point P. This is O1, this is O2.
Why can't P be the center of homothety?
And they can also be, of course, internally tangent. Yeah.
I wanted to ask that why can't P be the center of homothety?
Why can't P be the center of homothety? Well, you tell me, why can it be?
Because the ratio of this, it should be just the radius ratio, right? So there is
Right.
a ratio that takes it.
Yeah, exactly. So when we take this point P, obviously O1, P, O2 are collinear, right? You can just prove this by taking the tangent here, and then O1P is perpendicular to that common tangent, and so is O2P, and so they're collinear. And because they're collinear now, you get that PO1 by PO2 is equal to R1 by R2, and P also lies on like line O1, O2. And so P is the center, a center of homothety sending omega 1 to omega 2. And here it's the internal one, right? Because the external one will be like as outside over here, using the external tangents, things like that, right?
In a circular arrangement, how many centers of homothety can be there?
There are two, right? We discussed that. There's the x simile center and there's the in simile center. This one with
Like,
positive ratio and this one with negative ratio. Yes, these are also harmonic. That is correct. Because of the same reason. If this is Q, then QO1 by QO2 is still equal to R1 by R2. That still holds. And that's also equal to PO1 by PO2. So QPO1 O2 will also be harmonic. That's correct.
also, like, is there a way to prove that there isn't more?
We just discussed that, right? Over here. When we
Okay.
have segment O1, O2, it can either lie outside or it can lie inside. And depending on that, you have only one value of x because it's a linear equation.
Got it.
In some cases, you actually don't have any solution. That happens when the circles have equal radii, but let's ignore that edge case.
Because the tangents will be parallel. That's what.
Yeah, so they won't actually be meeting at any point.
Yeah, but in that case, there can exist a internal one, right?
Yes, there will be an insimile center in that case as well. And that would just be the midpoint of the two centers. Okay, so that's it. That's this for the externally touching case. What happens when they touch internally like this?
Same P is the center of homothety.
Right? P is still a center of homothety because you still have PO1 by PO2 equal to R1 by R2, except that this time it's external. Now, again, this does not mean there isn't an internal one. There still is an internal one. You just don't see it because there are no common tangents. And they are, like the other one would still lie over here somewhere, and you can get it in the exact same way. Got it? Okay. And of course, these four would be harmonic as well.
Wait, here only one will be there, or two will be there. I didn't hear it.
There will be two here as well. There are two in all cases except for when the two circles have equal radii.
How is the second? Where is the second one? In this case.
Yeah, let me draw it. So you have this circle and you have another circle. Two will lie inside, I guess. Yeah. So what you do is you just take two parallel rays as before, and you take this intersection, and this is your other center of homothety. And of course, note that if I take them both on the same side, I'll just get P as normal. So you get both of these. This is the external one, and or rather the x simile center, and this is the in simile center. So like I said, just because you can't draw those internal tangents does not mean the in simile center is gone or disappeared. It's still there. Sorry. Okay. Yeah. So with that covered, let's actually return to that problem I mentioned all the way at the beginning. Let me bring this to the end. Yeah. So we have to prove that we have these two circles which are tangent to the outer circle and this common line. And you want to show that these two meet on the circle. Does anyone have any ideas?
Yeah, they meet at the arc midpoint.
Okay. They meet at the arc midpoint. Arc midpoint of what?
The T prime T.
T prime T's arc midpoint.
Actually,
Okay.
you haven't put the points.
Yeah. So, okay. You can just ask me to mark. This is A and this is B, let's say.
Yeah, arc midpoint of AB.
Okay. Arc midpoint of AB. Okay. So before we just go into assuming something like that, obviously, like how does one think of that in the first place? So first of all, observe that if this circle, if I just vary it, if I choose another circle like this, another one, then all of them will have these 2 points, right? And all of them have to pass through a fixed point, simply because if I fix one of these circles, this point already gets fixed. And so everything else has to pass through that. And so I know that this point I'm interested in is a fixed one. And now if I be symmetrical about it, and if I select this nice circle right here, I'll find that it has to be the arc midpoint. Can't be anything else.
What's
Right?
the arc midpoint? What is arc midpoint actually?
The perpendicular bisector of AB would meet it in 2 points, and those are the 2 arc midpoints.
Oh,
Here it's the major one, the one not in the same arc as the circles. Yeah. Okay. So now we can actually get rid of this other circle now.
Sir, can you repeat this?
Or repeat. Okay. Wait. Yeah. One second. Okay. So we had these 2 circles, and we wanted to show that Tx and T prime X prime meet at the same point on the circle, right? So imagine I fix this circle. This one is fixed, and Tx meets this at some fixed point, right? Let's say I call that M. And now I choose various possibilities of T prime X prime. So all of these have to pass through this same point, which means that this point is fixed in general, even if I just take one, any circle, right? So if I choose my circle appropriately, if I choose it, the one that is symmetrical, so to say, so that would actually be the midpoint or the circle with diameter midpoint of AB and the other arc midpoint. Why should they pass through? I mean, you know that you have to prove it, right? And so knowing that this is true, you can just vary your choice of T prime X prime, and you can like observe that if the problem is true, then they must pass through the fixed point on the circle. And then when you select this good circle, which is like a nice special case for you, you get that the fixed point must be the arc midpoint. And so the problem in the end just reduces to proving that if you have one second, that if you have just this one circle, then Tx passes through the arc. Is AB the diameter? No, AB is any random chord. Okay, so how would we prove this? So obviously, given the title of the class, you can only expect that one has to use homothety somehow.
I think I have a solution.
Okay.
We can consider the homothety from point T that sends the internal tangent circle to the bigger circle.
Right. So let me name those omega 1 and omega. Yeah.
Yes. So when we send it the point x, wherever the point x will land, there the tangent will be parallel to AB.
There's no fixed argument that we're using to say that all circles pass through a fixed point. We know that this is true for any two circles, right? The statement had two very arbitrary circles. You weren't told anything about the circles.
We
Yes.
can intuitively think like if there's an AB in the big circle, we can consider a similar line like that in the small circle, which would be parallel.
Right. Okay. I'll get that. Yeah. Anyway, so here we have, so someone suggested considering the homothety centered at T that sends omega 1 to omega 2, right? And trying to locate where X ends up. So, like, where should X end up? X obviously should end up at some point that lies on Tx and as also the circle, right? So it should actually just be this point. So the point we're interested in, the image of X, it has to be M. It can't be anything else. So let's see why it should be that. So I have this point T and I have this X. And the only thing that I know how to understand about X is this tangent at it, which is AB, right? So we can observe that if T is sent to some point L, then AB goes to the tangent at L, right? We discussed this earlier. And there is one more piece of information that we know about lines AB and L. What is that?
Both are parallel.
Both are parallel, right? Because direction is preserved. So these two are parallel. So this is a tangent to the main circle that is parallel to a given chord. And that obviously only happens at the arc midpoints. And because we know it does not lie on T side of AB, we obtain that the tangent must be at the arc midpoint. And so Tx and the arc midpoint are collinear. Does that make sense? Any questions?
No.
Okay. So now I am going to discuss the 9-point circle. So imagine we have a triangle ABC. And let's say I mark the feet of altitude and the midpoints, MA, MB, MC. Then we have to show that these 6 points are consecutive. And of course, the hint is to use a homothety centered at H with factor 2. Okay, so can anyone quickly tell me where D ends up in a homothety with, centered at H with factor 2?
On the circumcircle.
Okay,
Like
well,
where
it would be the
AB
reflection of H in D.
Yeah.
And because this is 90, that becomes reflection of H in BC. And so because angle BHC is equal to 180 minus A, angle BH prime C would also be 180 minus A, and so it lies on the circle. Right? Okay. What happens to, and similarly, these would also end up on this circle. What happens to MA? Remember, we are reflecting over the midpoint of a segment. So that will produce a quadrilateral which has common, like whose diagonals have a common midpoint.
MA will also be on the circle, like you're reflecting H. So H over MA, that would be on the circle.
Why is that?
Because we have the quadrilateral. Okay.
Because that
One
will
second.
make a parallelogram.
Yes, exactly. It would form a parallelogram, right? Because if it because we're reflecting, if you have any triangle ABC and you have the midpoint of BC, and if you reflect A over M, you'll get a parallelogram. AB, A prime, C will form a parallelogram. So here, so in particular, angle BAC would be equal to angle BA prime C. And so angle BHC is equal to angle BH prime C again. And because that's 180 minus A, you'll get that this is cyclic as well. So, and so it lies on the circle. And of course, similarly, these also lie on the circle. These also lie on the circle. So all 6 of these lie on the circle. And because now if we reverse the homothety, which means we take the homothety centered at H with factor half, which is the inverse of the other homothety, you'll find that all 6 of these points end up on D, MA, MB, E, MC, F, right? And because the original 6 were concyclic, these new 6 must also be concyclic, which is exactly what we want to show. So this gets us 6 points on the circle. Can anyone tell me what the other 3 points are?
Midpoint of AS, BH, and CH.
Exactly. So because in the original circle, ABC also lying on the circumcircle, it means that their images in this new homothety will also end up on the circle. And those images are precisely the midpoints of AH, BH, and CH. Okay, so now we have these 2 circles, right? This circle and this circle. And H, what is H? Can someone tell me what H is? Is it the X simile center or is it the in simile center?
X simile center.
Right, it's the X simile center because the factor is 2, right? That sends the 9-point circle to the circumcircle. And so this is the X simile center. Okay, let's say we mark the center of the 9-point circle and the center of the circumcircle. Can anyone tell me something about H, N, and O?
They are
H
collinear.
Yes, they will be collinear. And
HN will equal NO.
sorry.
HN will equal NO.
Yes, that's right. Because in this homothety, O maps to N. The center should map to the center. And HO by HN will be equal to radius of circumcircle divided by radius of 9-point circle, equal to ratio of similitude, which is 2. And so you get HO by HN is equal to 2. And so HN is equal to NO, or N is the midpoint of H. Right? Okay. So that means H is the X simile center. And in fact, one more thing to note, the radius of the 9-point circle now is half of the radius of ABC. So if this has radius R, this has radius R by 2. Okay, so H is the X simile center. But obviously, even though you can't draw internal tangents to these 2, there is an in simile center. So what's the in simile center? Okay, so I will actually, I think, leave this as an exercise to figure out, because I think it's an interesting thing to try and figure out where the in simile center is. Yeah.
Is it the point itself? No.
Is it the point itself? I'm not sure what you mean.
Is it the point itself? Like is it H?
How can H be both an X simile center and an in simile center? The
Yeah,
ratio
okay.
has to be
I
negative,
see.
right?
Okay.
Yeah. Okay, no, I think I will leave this as something to figure out, because it is not very hard if we just follow the definitions over here. You have to find a point on OH such that, in fact, anything works. You can even use the trick of finding 2 equal parallel lines from the centers and try to use that. Or you can even try to use the harmonic bundle idea. It's a very familiar point.
Is it a centroid?
Yes, that is correct. It is the centroid.
Okay, I did from Euler's, right?
Sorry?
Because like OG and H have the ratio 2:1. So
Yes, exactly. So that's the same ratio that you come up with here. So G is the insimile center of the 9-point circle and the circumcircle. Yeah. Okay. Okay. Yeah. Let me just mark it now that the cat's out of the bag. Okay. I think we can move on, or rather discuss a few problems before returning to some more theory. Okay, so this is the first problem we'll discuss. Let me draw the diagram. So we basically have a triangle ABC, PQ such that PQ is parallel to BC, and you choose X on segment BQ so that AXP is equal to XCB. Actually, let me draw this in bold because that will make it clear. Okay, so you get AXP is XCB and you have AYQ equal to YBC. And what we want to show is that AX is equal to AY. This problem is very hard to solve, I think, if one does not have Homothety in mind. Because the angle conditions are extremely artificial. Right? Like, why are those two angles equal? AXP and XCB. But there is a way to make them much more approachable, which helps in solving the problem. In fact, if you think about it, it's also pretty difficult to construct such a point X, right? If I gave you those points A, P, B, C as they are given, and like, okay, the full structure with ABC and a parallel line PQ, it's still very difficult to construct X on segment BQ such that AXP is equal to XCB. Okay, so does anyone have any ideas?
It seems that we should prove triangle APX and BXC similar somehow. Like I don't know how, but it seems that it is the way.
Sorry, can you repeat the triangles?
APX and BXC. Like they are seeming to be similar.
Okay,
But I currently don't have a proof.
I see.
I symmetrically can say the same for AYQ and I think BYC.
Right. Well, not BYC, CYB.
Oh, yes.
So this is a good conjecture because it might help us in figuring out some angle conditions which might help us potentially angle chase, and somehow maybe we'll find some cyclic quadrilaterals, and then we can expect something will happen and we'll have AX equal to AY. Right? So this is a very natural conjecture to try and assume that, okay, maybe the angles are good and I just need to figure that out. So this is a good idea. But does anyone have any more other ideas that involve homothety?
I think um, we should consider the homothety of x uh, with respect to a.
Okay. So we have some interesting ideas. What is the center of the homothety?
Um, the ratio, the center will be a, and the ratio
Okay.
should be um, AB by AP.
Okay, got it. And yes, we should note that this is also equal to AC by A. So basically, we're interested in the homothety centered at A that sends segment PQ to segment BC. And you want to consider the image of X in that, right?
Yes,
Yeah. So
and that
here
gives
it
us a
makes sense
cyclic
because,
quad.
yeah, sorry. Someone was saying so.
And that gives us a cyclic quad, I say.
Okay, yeah, we'll get that. So let's talk about some motivation behind why doing this homothety is an idea one could even consider. So first of all, something we should realize is that A is the A is what's creating trouble, A and P, right? XCB is an okay angle. It is still doable because like B and C are what the vertices of the triangle, so you have some control over them. But A and P are just away from this whole configuration. And also you have PQ parallel to BC, which you have no idea how to use, right? So in some sense, X is like trying to link itself with P and also with B and C, but it's not really succeeding because of A, something like that, right? And so because of this, it makes sense to transfer this angle AXP somewhere else where it can do a better job, right? And the easiest way to fix that is to send P to B because that removes P first of all completely. And it maybe gives you some other point, but now the angle itself, it can be better classified using only 2 points X and B, which you already know. So when we do this expansion and send X to some point X prime, so note that BX prime will be parallel to PX, right? So in that case, we have this angle equal to this angle. And now, as was remarked, this is a cyclic quadrilateral. That doesn't pass through Y. Or rather, we don't know whether it does or not. But yes, so this is cyclic. So this is very good, right? Because now you know that X is, sorry, because now you know that X prime BC concyclic, which is something better than before, right? You're actually able to make sense of that angle condition somehow. How do we proceed from here? How can we understand the point X prime better? Because we still don't know much about it, right? We only know that BX prime is parallel to PX and it lies on AX. In fact, the whole trouble is arising because of line AX, right? We don't understand A at all. Right now, we are only like friends or something with BXC and potentially X prime. But we do need to figure out something more about X prime before we can actually use that. So we know about x prime with b and x, right? What we don't know anything about x prime with is c. Can we say something about cx prime?
Parallel to QX.
It's parallel to qx. Yes, that's right. This is going to be parallel to qx because q goes to c and x goes to x prime. And so qx is parallel to cx prime. So now we have this cyclic quadrilateral. Okay, let me actually use a different color so that it's... We have this cyclic quadrilateral. And these two are parallel. So what does that tell us?
It has to be isosceles.
It has to be isosceles, right? So what can we say because of that?
Bx prime is equal to xc.
Sorry?
Bx prime is equal to x.
Yes, that is right. Bx prime is equal to cx. Anything else? Remember, bx prime is not very interesting for us, right? Let's think about the length that we actually want. So remember that we want lengths on line AX, right? So we should try to relate that somehow.
I think the diagonals will also be equal. So BC is equal to x.
Exactly. BC is also equal to XX prime, right? So we have BC equal to XX prime. Can anyone finish the proof now? So let's say this ratio is K, right? So I know that I had A and I had X and I took a homothety at X with factor K and XX prime had length BC. So can I compute AX using this? If the ratio is K?
That would be BC by.
Sorry.
It would just be BC.
Your voice keeps getting cut off.
I think it should just be BC by.
Can anyone else hear what he's saying? It keeps getting cut off for some reason. Okay. Anyway, so AX prime will be equal to K times AX, right? And so XX prime is equal to K minus 1 times AX. And because we know XX prime equal to BC, we get that AX is equal to BC by K minus 1. Can anyone finish the proof now?
Yeah, like a symmetric argument for y.
Exactly. Now, exact same argument will work for y. And because K is symmetrical in both, you get AY equal to BC over K minus 1. And so the two lengths are equal.
Could you please repeat the motivation for homothety? Why we thought of that?
Yeah. So the reason behind that is we have two very artificial angles being equal, right? AXP is just extremely weird. XCB is maybe manageable, but AXP is just very bad. And the reason for that is neither of the lines AX or PX you know anything about. They're just weird. Whereas in XCB, at least BC is good. And CX also, and the angle is also at a vertex. So that already makes that angle even better in some sense, right? which makes AXP really weird. And the only thing that ties together these two angles is X. Right? And the trouble is that A and P are not involved with triangle XBC too much.
Okay.
So what you try to do is you try to send this angle to another equal angle so that you eliminate P and A from the business. And the way to do that is by taking a homothety centered at A that sends PQ to BC. Because now P goes to B, X goes to some other point, some new point which you're introducing, some another point we don't know anything about. But now you get X prime B, which actually eliminates everything like AP. And everything is just using B, X, C, and some new point. And because you're lucky, it turns out that this homothety produces a cyclic quadrilateral. And because you have some other parallel conditions, which helps you to relate X prime with the rest of the configuration, you're able to get XX prime equal to BC, at which point you're done. Because now you can compute AX in terms of BC and this common ratio, and that will just finish. Yeah. So in extremely symmetrical, because see, if you repeat the argument with y and you get some new point y prime, you'll get that b, y prime are also concyclic. Maybe on a different circle, maybe on the same circle. That does not concern us, right? So you'll get that they're concyclic on a different circle. And now y prime will also be equal to bc because that too will be an isosceles trapezoid, right? And so now it just becomes something like you have a, x, and y, and you have x prime and y prime, and you know that these two are parallel, and you know that these two are equal. So you actually end up getting that this is isosceles. These are all equal to each other. And so x is a y. That is basically this argument. Okay, any questions?
No.
Okay. So continuing the theme of having trapezoids in the problem, let's do an isol problem. I think, yeah, it will be somewhere. And we have to show that angle BQP is equal to angle DAQ. Okay, so again, this is very weird, right? It has a very artificial setup again. You have BQC being equal to AQD, and they don't make sense together at all, right? So does anyone have what the first step should be? A reasonable step? Should we join the two non-parallel lines externally? Okay, so doing that will introduce another point. But instead of thinking about trying to imitate what we did last time, you should rather think about what is it that you exactly want, right? What is the trouble we're trying to get rid of? BC, so we have BQC and we have AQD, and we don't have any way of making sense of those two. right? So in some sense, we want to bring B and C to A and D, right?
Yeah.
Homothety
So we
at
could
D.
Yeah.
maybe we could look at some similar triangles.
Okay. Which two triangles are similar that you're interested in?
Think one second. Think it should
I
be
think
yeah, you go, please.
Okay. Or is someone else interested in things?
It's because it's like I was thinking something about the circumcircle of BPC and APD.
APD. Okay. What about them?
So I noticed that since it's a trapezium, angle CBP is equal to angle BPA, and if you do some homothety with those two triangles I mentioned before, maybe that could be the finishing argument or something. I'm not sure. I don't have a
Okay.
complete.
So you want to introduce AB cap CD. Let's call that R, and you want to consider the homothety that sends BC to AD.
Yeah, maybe.
Okay.
Okay, so we
So,
could look at triangle BPC and APD then.
okay. And what about them? They're similar, yes. And
So uh, like we need to prove some angles are same. So like P goes to D and C goes to A.
yes, yes, exactly. So the point is both ideas are good because we want to send segment BC to segment AD so that the angle makes more sense, right? So it's a very natural first step. But the problem with the R approach is that you have to introduce a new point first of all, which is not even there in the picture. And also because when you do that homothety, you're interested in where Q ends up, right? So in the statement, very inherently, you will also have introduced the line RQ because the image of Q will lie there. And you cannot make sense of QP alone, forget RQ, right? RQ is just another problem you're creating for yourself. And the benefit of using P instead is that you already have line PQ in the statement using angle BQP. And so it makes sense to introduce this. And so if we simply look at the negative homothety that sends C to A and B to D, it will send Q somewhere as well, right? Let me use a different color to illustrate that better. So it will send that somewhere as well. Let's say this point is Q prime. And now what do we know? Because BQC is equal to this angle, this is also going to be equal to DQ prime A, right? Can anyone tell me what that means? No?
We
Q
could maybe
dash
prove
A D and Q would be cyclic.
The cyclic.
Yeah, exactly. Now we end up getting that these 4 points are concyclic. Right? Okay. And now let's take a look at what we have to prove. We have to show angle BQP. What has BQP become in the new picture?
Like D Q D
DQ,
DQP.
DQP, right? Yeah, because P stays at P, right? P doesn't move. So it becomes angle DQP, okay, which is equal to angle DQQ prime. And we want to show that this is equal to
DAQ.
DAQ. So are you sure that this reduction is correct? In particular, this step, is it correct? B goes to D. Where does Q go?
Q goes to Q prime.
Q goes to Q prime, right? Not Q itself.
Yeah.
And so this angle is angle DQ prime Q. And we want to show this is equal to angle DAQ. And does anyone see the finish now?
Yes.
You want to show that this
Yes.
angle and this angle are equal. Yeah. Anyone?
Angles in the same segment.
Sorry?
Angles in the same segment.
Angles in the
Exactly.
same segment.
Now, because it's
relative
cyclic, you're
right?
done. Because now you have
Yeah.
angle DAQ equal to angle DQ prime Q. And so all this problem took was just one homothety. We were one homothety away the whole time. And the entire difficulty of the problem lies in figuring out which homothety is best. Or how should I go about this rather? Okay, any questions? Okay. So now we'll move on to a slightly easier problem than what we have had so far. So imagine we have a circle and another circle supposed to be tangent. And suppose they're also tangent to this. Let's say they're tangent at a point X. So we have to prove that angle PXQ is 90. Okay, so does anyone see a very direct
Like
approach?
if we do the tangent at X and then it meets at the midpoint of PQ.
Exactly.
So like if we call it in, then yeah, in the angle chasing rate.
Yes, that's a good solution. So one approach is to just take the tangent at X, and we know that it meets PQ at its midpoint. Why is that? That is because mx squared is equal to mq squared is equal to mp squared, right? And so you get that mp is mq and so m is the midpoint of pq. In fact, you get that m is the center of the circle passing through px and q. And because pq is a diameter, we get pxq is 90. So obviously there is no homothety there. So this is a non-homothety proof. Now let's discuss a homothety proof for this.
Is M the midpoint?
Yes, m will be the midpoint of pq. Okay, so imagine we take a homothety at X that maps omega 1 to omega 2, the smaller to the bigger. And let's say we look at where Q ends up. Let's say that's Q prime. So what do we want to show? We want to show angle Q prime X is 90, right?
Yes.
So what does that translate to?
We have to parallel tangents, one at P and one at Q prime. So I guess
Sorry, could you come again?
like we have to parallel tangents, one at P and one at Q prime. So Q prime and P is the diameter.
Yes, exactly. So the proof here is that the tangent at Q, which is line PQ, maps to another line parallel to PQ. And this must be the tangent at Q prime, right? And so in omega 2, you get that the tangents at Q prime and P are parallel. And that only happens when they're diametrically opposite to each other. And so PQ prime is a diameter, and you get that this angle is 90. Okay. Now let's move on to the last piece of theory that is important and is useful very often. And that is Monge's theorem. So what Monge's theorem basically says is that if you have three circles and you take their intersection of their common tangent, so what I'm really doing is I'm considering their x simili-centers, right? Then these 3 points will lie on a line. And the proof of this fact relies on this very important result, that the composition of two homotheties is another homothety. I won't prove this here.
We can also just do it by x simili-centers in the radii.
What do you mean? I'm not sure I understand.
Like the converse of Menelaus.
Yes,
Yeah.
yes, that is correct. We can use the converse of Menelaus. That is true.
We'll have the ratio of radii. Like if like the center of omega 1 is O1 and like it meets at some point on the line at some P1. So like
Yes.
same for the omega 2 and omega 3. So we'll have a ratio and
Yes, that
like
is true.
it'll
We'll have
multiply to
ratios
1.
and yeah, yes, exactly. So in fact, this fact right here can also be proven using mean loss. So I invite you all to like try and figure that out. So here I'll just discuss a fact which uses this, which is in some ways a little more general than mean loss, even though it can be proven using it. And it provides for a nice solution to this problem. So it's like, let's consider the homothety that sends omega 1 to omega 2, right? Let's call this H1, right? And let's consider another homothety which sends omega 2 to omega 3. So if I take a point P, and let's say I apply H1 to it, and I apply H2 to it, let's say P lies on omega 1, then it will go from P to some point over here, and then it will end up on omega 3, right? This is how P is moving.
And H3 must lie on H2, H1.
Sorry?
Like for this to happen, we need that H3 must lie on H2, H1, where H3 is the composition entity.
Yes, that is right. So this itself, if I treat it as some new H, it's also homothety, right? And it sends every point on omega 1 to some point on omega 3. And because this is an important part, because people get confused when some of the x simili-centers become in simili-centers because the argument doesn't always work through. For example, if you take all three in simili-centers, that's going to fail. That won't work, right? Okay. Anyway, so what happens here is that because omega 1 to omega 2 has positive ratio, and this also has positive ratio, their composition will have ratio as their product, which is still positive. And so this new H is a homothety with positive ratio that sends omega 1 to omega 3, which means that its center must be this other point, right? So let's say this is centered at, okay, let's call this P, Q, and R, right? So we know that this is centered at P, this is centered at Q. And we know that H is centered at R. And now the trick is to observe that the line through the center, or rather line PQ, is preserved in both of these homotheties, right? When we expand, or sorry, when we take a homothety at P with a certain ratio, line PQ is preserved. And then when we do it again from Q, line PQ is still preserved, which means that this H also preserves line PQ. And if a line is preserved in a homothety, that means the center of that homothety must lie on that line. And so R has to lie on PQ. And so these three are correlated. In particular, this result is still true, even if you have two insimile centers and one exsimile center. You have to have an even number of insimile centers. So either you have three exims, two insims and one exim. And of course, this one exim can rotate over all three PQ and R, and you'll get corresponding interior points. These other cases can also be proven using mean loss, but of course you have to use signed distances. And the reason this even is required is because this argument, this part of the argument will not work through unless the product of these two matches with the third one, which can only happen when exactly two among them are, sorry, when when even number of them are negative, because the total product needs to be positive. And if you have all three negative, that's an issue, or exactly one negative. And of course, this is true even when your insim, like I said, cannot be constructed using internal tangents, right? Even if all three circles intersect, some version of this theorem is still true if you can figure out the insimile centers by using that argument. Things like that. Any questions?
Do insimile centers always exist?
Yes, we discussed that, right?
Okay, so insimile centers always exist, and there is only one case where exsimile center does not exist. Like
Yeah, and
that
that's
is
when
when
the
the
same
ratio
rate.
is radius is equal.
Yeah.
Okay.
Right. Okay. Yeah. So I think we can discuss one more thing and then I can wrap it up. I think I am a little behind schedule here, right? Okay. I'll just wrap it up with this one last fact that is useful. Okay, so let's say ABC is some triangle and this is the circumcircle of ABC, and you also take the incircle. And let's say the incircle touches the side lines at D, E, and F, and the arc midpoints are MA, MB, and MC. So we have to prove that MAD, MBE, and MCF are concurrent. Yes, that works. So so someone mentions that DEF and MA, MB, MC are homothetic. Why is that? Okay, so EF is perpendicular to AI, right? And what about MCMB? We know that MBA is MBI and MCA is also MCI. And so MBMC is in fact the perpendicular bisector of AI. And so that is also perpendicular. So you get that MBMC is parallel to EF. And similarly, you have this for the other three sides as well, DE and MAMB and DF and MAMC. And so you end up getting that DEF and MAMBMC have all sides parallel, corresponding sides parallel. And so they have a center of homothety, which is at this concurrence point. Now, the reason this is actually so useful is because this point also lies on line OI. Can anyone quickly prove why that is? Okay, so this homothety maps MA, MB, MC to DEF, right? So let's say we consider where O ends up. Let's say that's O prime. So because O is the center of MA, MB, MC, O prime must be the center of DEF, which means that O prime must be equal to I, which tells us that this point, let's say we call it X, X, I, and O are collinear, which tells you that these 4 points concur. Now, can someone quickly tell me what happens? Something special about X actually. Yeah. X sends the incircle to the circumcircle, right? Because DEF go to MAMBMC, and so circle DEF goes to MAMBMC. The circumcircle ABC. And so X is the center of homothety sending the incircle to the circumcircle. So can anyone tell me whether this is the X simile center or the in simile center? In fact, note that yes, it's the X simile center, and that's because we can see that if you draw these two rays, then this is actually just that all over again, right? You have two parallel rays, and this is 90, right? And so they intersect at, sorry, they intersect on line OI at the X simile center. How can we locate the in simile center? We take the opposite arc midpoints, the main arc midpoints, right? And then D, NA, E, NB, and F and C, they will all concur at another point, and this will be the in simile center. So these satisfy a lot of properties. I won't go into all of them here, but this is like an introduction to them, I guess. Another thing to note is that another way to prove rather that this is the X simile center is that or rather directly is that let's say we define X as the XM that sends incircle to circumcircle. Then where will D go? D will go to some point on the circumcircle, right? And the tangent at D, which is BC, should remain parallel to BC. And so it goes to some line which is parallel to BC and tangent to the circumcircle. And because we're considering a positive ratio here, it has to be this one. And that gives an alternate for why these three concur at X. Okay, so I think we can stop here. Yeah.
Should I stop recording?
Yeah.
Okay.